I'll wait until they... Welcome to the CERIAS seminar for March 2nd. Today I'm honored to be able to introduce Professor Anupam Joshi, who comes to us from the University of Maryland, Baltimore County, where he is the Oros family professor.
Soros family might have been even better.
Oros family professor, chair of the department and director of their cybersecurity center. How he has a distinguished career, but that brings distinction not only to the University of Maryland, but also to Purdue. He started his career getting his PhD here at Purdue, and has since spent some time here as visiting faculty at the University of Missouri before he was stolen away by University of Maryland. So I will turn it over to Professor Joshi.
Thank you so much, Chris. It's an honor to be back, to see all the changes. And it's a dangerous thing to be lecturing in front of the algorithms guru, who taught me all about the PRAM model. I still remember it. So I'm going to talk about, well, you see the topic there, but I was told that this is an interdisciplinary audience with not just a bunch of hardcore comp science people. So the talk will be pitched that way. If you think it's getting too far away and you want some technical details, all you have to do is to raise your hand. So here are the things that I want you to remember. First, the traditional access control models are inadequate in many circumstances, and you'll see why I say that. So that's what's wrong, and then there is, well, what's right. So context-aware and policy-driven approaches can make sense for complex security and privacy situations. Policies, and that's self-evident. Most organizations have policies. You know, if you go to ITAP at Purdue and say, well, what's your security policy? They'll produce a document. When you sign up for an account at Purdue, you get this big, I don't know if you read it, but you get this big stuff to read.
Would you like to use this?
I can.
Yeah, if you want to just flip.
Yes, I can do that.
1 second.
Yes. Thank you. So, so policies can be captured in a form that computers can understand, right? Not pieces of text, but ways that computers can ingest and reason over. And I'll illustrate this using 3 scenarios: mobile security, intrusion detection, and vehicular security. I'll spend most of my time on the first one, mobile security, but as time permits, I'll move on. And as typically happens in these talks, I have way more slides than we have time. So I'll be selective in what I tell you. Some of those are details that may not make sense. So let's talk of mobile device security, right? So I'll start with the last statement, and I'll promise you that this slide is about 2 years old. So we've been saying this for a while, but now it's famous because Tim Cook said it. You know, when he was contesting the federal government warrant on unlocking the cell phone of that person who committed the atrocities in San Bernardino, you know, they're basically saying, oh my God, your smartphone knows so much about you. If the government gets access to it, it's disaster, right? So without offering an opinion on that particular thing, the point is that your smartphone knows a lot more about you, right? Broadly, these have been used for participatory sensing systems, where our phones are individually collecting data, but then collaborating in some way to do better things, and which is great, which is fantastic. Fairly simple things. Forget the complex sensors that are engendered by Internet of Things, but Microsoft Research did an experiment about a little less than a decade ago now in India, where they were trying to estimate the amount of traffic on the road. And it's very hard to put sensors, right? And they cost a lot. So what they did was they built a little app, turned on everyone's cell phone mic, and they recorded the amount of honking you were hearing. So for those of you from India, when you are stuck in a jam, you honk. You know, when you don't find your way, you honk to see if people will give way. And simply by measuring the amount of honking noise, the amount of noise you're hearing from horns, they were able to very successfully predict the amount of traffic on the road, right? Great example of participatory sensing. But that's a simple example. Just think today of how much information my phone through GPS knows where I am. Through proximity, Chris's phone probably also has a Bluetooth device. I can sense his Bluetooth MAC ID. I may not know who it belongs to, but I have a sense of who it is. At least traffic analysis can be done. My phone has Google Calendar, which says what I was doing. It actually read my email, and Google very helpfully read my email and said, oh, you're staying at this hotel in Indy tonight, and inserted that into my calendar. Right? So there's a lot of information that exists. So the thing is, smart mobile devices know a great deal about their users, including their current context. Acquiring and reasoning about this context helps them provide better services. That's why we allow them. And also sharing this information with others can be good. So what we are trying to do is to say, let's leverage this idea of context and make the protection policies context aware so that you can limit not just information sharing, but actually access to the actions and information. Right? So we're sort of trying to say, let's leverage this context piece. So what do we do? And you'll see some details later, but we use declarative policies that can access the user's profile and context model for privacy and security. One of the things we do is to limit information sharing. So in certain situations, we'll share some aspect of the information. But we also use the same policy infrastructure to control actions. Things like you're not allowed to have your phone ring while you're listening to a talk. I mean, that's an action control. Right? You know what part of the world I come from when my slides say Fort Meade. Or at least Chris knows what part of the world I come from. And what agency that is certainly interested in privacy, but from what perspective, we can argue that we interact with a lot. But but forget that. Simple. Permit Facebook uploads while at home, but not in the meeting. Right? So these are kind of things you would want to do. So for that, you first need to figure out, where I am. And traditionally, if you look at the phone models, they have been like, you're at this GPS coordinate. But we're talking about something much richer. I'm in Purdue University, which is in West Lafayette, which is in Indiana, which is in the United States. I'm participating in a talk. You can infer that from my sensors. Chris was here, Elisa was there. I met Elisa, I met Aniket, Dr. Atala is there. So, there's a bunch of people here. I can figure that out. I can figure out that I'm filling a speaker role by scraping the web. Somewhere in the CERIAS webpage, there's probably an announcement that says I'm going to give a talk today. I just have to scrape the web, and I have that. So what we do is we define an ontology to capture this rich notion of place. The distinction we're trying to make is GPS coordinates are a position. What you're really interested in this context thing is a place. So what is a place? It's a conceptual place. It's around what location you are in, certainly, but what activities you're doing, what roles you're playing in those activities. And so activities are called at places and involve users filling particular roles. So we capture this kind of information in an ontology which we can instantiate from the sense data on our mobile devices. Right? And then this, I'll skip this, but it begins to look something like this once you put it in notation 3. So what I don't want to spend time today on is how do you go from this kind of low-level sense knowledge to higher-level context. We have done some work, but there's a rich body of literature of people whose job is to say, if I see this information from your sensors, then this is what you must be doing. Right? What I'm trying to do is to say, how can I make this affect privacy? And I'll start with, okay, this picture is old, but nothing much has changed. Right? So if you look at the current version of Android, and I'm going to pick on Android because that's where we do a lot of our work and our development, because it's easy to do. What happens when you install an app?
It asks for permission.
It asks for a bunch of permissions, and what do you do?
Yes. Times out of time.
Right? I mean, I've done this kind of thing in places where there are fairly senior security aware people sitting, and most people will go yes. How many of you even know that in the latest version of Androids, you can retroactively remove permissions. And this is an audience attending a security seminar. Imagine what is happening.
I don't have this version of Android.
So you need to go to the latest version of Android. But again, just speaking on Android, but the same thing is true in iOS, the same thing is true in Windows 10 or whatever else. The model is at install time, I will ask you for a bunch of permissions, and from then on, those permissions stay static. So what we are trying to do is to stick something into the Android framework. I should really draw a diagram, a box below here saying the Linux kernel, because for some things we need to do, they're better done in the Linux kernel. We're trying to stay away right now. Because one, it complicates things. You have to do a kernel compile in addition to an Android framework compile and then a routing. But for the computer science types amongst you, imagine there was a box that said Linux kernel and some of the stuff could happen there, right? So you basically stick things in between that take the part that is doing the context reasoning to figure out what the context is, take the policies that are coming in, and so you have some knowledge base that have policies that are applicable in various contexts, and then you reason over it to decide whether an action is either allowed or not allowed or allowed in some generalizable form. Right? So I'll make that clear in a little bit what I mean by that. But you have the policy decision point, and then you have a policy enforcement point, and that enforcement point could do generalizations. And this is what, so if you go back a few slides, this is what it actually looks like to the system. Now, we're not user interface people, but even we recognize that telling even a computer science person to say, write something like this up to describe what your policy is not going to work. So what you have is things like this, where we can read the underlying ontology automatically and populate a user interface saying the places of interest in Purdue are Lawson Building, whatever the Memorial Gym is called now, Stewart, PMU, so on and so forth. Or if the same thing shifts to a different university, we can instantiate what this is. We can instantiate the activities that have to be controlled. We can instantiate the devices that have to be controlled. And we provide a little user interface that it's not the best design user interface, but the idea is that it's a user interface that lets you compile down those policies. Let me come to that a little bit later. So this is an example of what that interface looks like. And then what can happen is, and this is just some screenshots to show you that the system works, is that as the request comes, we dynamically reason over the policy and the context to decide whether to permit or deny it. Now, one of the criticisms that you run into when you do this kind of sort of AI meets security work is this is too heavy. You can't run it on your mobile device. It'll eat all the battery. It just won't run. But we've done significant experiments by running a Jenna prototype on Android. And we've been doing this for the last 3 or 4 years at least, where there is very little battery, extra battery drainage. So what are the kind of, let me give you some examples of the kind of policies that we're talking about, and then I'll show you in a little bit how you actually implement them. For a moment, I thought I had the wrong slides. So imagine that you're a student here. I don't see too many undergraduates here, but put yourself in their shoes and imagine that your parents are paying for your education, right? They might want to know whether you're attending classes or not. And so they might want to query your device saying, where is so-and-so right now? You might want to write a policy. So right now you have two choices, right? When you install the tell my mom where I am app, you can either give it the permission to see what your location is or not give it the permission to see where your location is. And if you say no, bad repercussions. So what you really want to say is, yeah, if it's between sort of normal school hours and I'm in the class that I'm supposed to be in, then, right? And now notice this is very different from a standard access control model. And what I'll show you later is it can be ground down to that. We come of it sort of from a standard full first order logic model, but we can ground this out in a little bit in the security models. But that's what you really want. And that's what we are permitting. We're letting you write these policies, and then we build this thing in between. So now for the security-oriented folks amongst you with a little bit computer science background, we do both mandatory and discretionary control. So what you're seeing is an example of a discretionary control, right? You decide, you control your location, you decide who to tell it. But we also permit mandatory policies to come in where Purdue has issued you a laptop or a tablet or whatever, and Purdue might have some policies saying, if the Professor Prabhakar asks where a faculty member is at any given time in his department, that information must be reported accurately, no matter what the user has said, right? So you can do things like don't share a user's context if they're in a particular place. The other thing that I was getting at earlier is, so go back to that example. That may be the easiest way to think about it. Go back to the example of my mom is asking where I am right now, where I'm supposed to be in a class, but I'm actually hanging out in Chauncey Hill, right? So traditionally you see two options. You can write a policy that says don't give her that answer or give her that answer. We permit a third kind of policy that says tell her I am in Lafayette or West Lafayette, which is a correct answer. But it generalizes the response and obfuscates it, right? Now I'll be honest and confess that we're not the obfuscation researchers, but there are enough people who have worked on how you want to generalize and obfuscate, and there's some of them sitting right here, right? So the idea is we write the policy on top that says obfuscate. And for spatial and temporal things, those obfuscations are trivial and straightforward, right? I mean, you can see them yourself. I could say I'm in this room, G52 or whatever it is. I could say I'm in Stewart. I could say I'm in Purdue. I could say I'm in West Lafayette. I could say I'm in the spatial generalizations are obvious. The temporal generalizations are obvious too. What we also build in our system, and this is what changes domain to domain, is capture in ontologies generalizations for other kinds of activity classes. So we're able to say, I'm giving a talk right now, or I'm working right now, or I'm busy right now. All of these are correct answers. They're generalizations of the correct information. And this is an example of that where you have to build. So I mean, spatial and temporal are obvious, but you have to build this. The other thing we build here is sort of a visibility model, right? So it's a more nuanced model that I'm describing to you right now, but I don't necessarily want to get into that level of technical details, where what you're saying is you can define classes of visibility and then have these things associated with visibility. So in addition to having a hierarchy of activities, for example, you can also ascribe visibilities and subclasses of visibility to each of these. And they don't have to be at this, I mean, you don't have to say everything at this level is completely private and everything at this level is, public. You could ascribe hierarchy visibility labels to different points in the hierarchy. Okay, so this is, I think, what I was describing to you a little bit earlier. Share GPS coordinates only if I'm in my office, and so on and so forth. So how does this work? So one of the contributions is how do you write these policies in ways that will make sense to a security. So when we started this work, we would do this, and I'd go to a security type conference or seminar like this one, and someone would say, well, you just said access control. So is this RBAC? Is that RTBAC? Is that, whatever one of those flavors? What kind of access control are you talking about? Right? So, and our answer was, this is more complex, but if the closest you want to come to it will be something like attribute-based access control, because you're defining arbitrary attributes and deciding access based on that. So the formal methods we use is we write ontologies in OWL, and then use specialized mechanisms such as Jenner rules or swirl or RIF or Ray, and we've used various of these in the past. For those of you who are not familiar, this is public domain now, but came out of research in HP Labs. This was a W3C innovation. This was another W3C innovation. This is what we did with our former student, Lalana. She's a principal research scientist at MIT now and has been developing this model further. So all of these inherit formal semantics that are grounded out in logics, typically modal logics. So Ray, which is the work we did, was grounded out in modal logics where everything would be reducible to obligations, dispensations, and things of that nature. But as I was saying, we've now worked to ground these out in security models. So we did some joint work with Ravi Sandhu a few years ago, and his colleague Will Winsborough, who unfortunately passed away, which was in SACMAT, which shows that you can use these kinds of policies that I was just writing and essentially capture the entirety of the role-based access control model. So if you want to restrict yourself to RBAC only, you can write policies that make sense. We're now working on attribute-based access control. We've done the ABAC alpha model and just published it, and we're almost done with showing that you can capture the ABAC beta model. And if you want to understand, so let me do a quick survey. How many of you here know about attribute-based access control or role-based access control? Is that my phone? Yes, it is my phone. So not everyone. Right? Who doesn't know RBAC and ABAC and things like that? Oh, just one person. Well, then you can ask your friends, right? But the short and long of this is, ABAC is basically saying people with black hair should be allowed to access something. Right? RBAC is saying full professors in the department should be allowed to access something. And otherwise, everything is reduced to the individual user, discretionary or mandatory control. So I apologize for this slide, and you see my other alma mater's logo there because this is I spent a sabbatical year there, and I'm actually supervising a student. This is IIT Delhi. So this is some work that was done by Ravi Sandhu and his student. Shin was, I think, the first author that proposed the ABAC alpha model, which said, look, there are users who have users attributes. Users create subjects, which have subject attributes, which they inherit from the user. And then there are objects with object attributes. And then you have a policy and an authorization model. Right? So can you write policies in our language that will capture this? And the answer is you can. So then that's the next quiz. How many of you have heard of RDF or OWL or? Two people. Okay, this I might have to, well, three people. This I might have to say. So RDF was a proposal from, who's heard of the semantic web? And just a few more people. Knowledge rep, just frames. And I mean, you remember frames from your AI class? KR? No? Some people do. All right. So a quick version of this is a way to capture ontologies, which are formal ways of representing things in the world and relationships between them. Right? There is a thing called a user, and then there is a thing called an object, and a user has certain access rights to an object. You have to write this formally. So when we are reducing ABAC alpha, we're creating and this is something called notation 3, which is you can write the same gobbledygook in XML, which is what gets a computer to consume it. This is just an easier way for humans to read this. So you're saying a user is a class, a subject is a class, an object is a class, and a permission is a class. A user attribute is a property that is defined on a user, etc. Then there is an action, right, which is a class. And notice what am I saying? It's action has a property that it's subject, and it's a functional property whose domain is action and range is subject, and it has another property. What is it? It has an object, right? So there's a subject and an object. With every action, there is a subject requesting that action on that object. So you're beginning to formally capture these kinds of things. So simple things, discretionary access control, right? Discretionary access control is Joe is allowed to access something, and you have readers, you have writers, things. You can define various action classes that you want, but here are two kinds of attributes. And what you can do is you can say this. You can say, essentially, this is your policy to capture DAC. It says an object can be written only by subject whose users are in the writer list of that object. And this is how you would capture it in our framework. So what we're showing is that this kind of framework of writing policies, and we want to write very generalizable policies, but to have this make sense to the security people, you want to be able to show this grounding. And for discretionary access control, it's easy to show. Mandatory access control becomes a little bit harder, but you can do it. So in this case, hopefully people will remember from their security/distributed operating systems class, right? The Bell-LaPadula model. And now this is writing an ontology to capture the Bell-LaPadula model. And now this is your policy. Right? A subject is allowed to acquire a read permission on an object only if the object sensitivity is less than or equal to the subject clearance. You can capture that in this framework. I will spare you some details, but for those of you who have done a security course and have done RBAC, one of the big things is say the static separation of duties, right? Which is basically saying that a person who is a citizen cannot also be a permanent resident. You're either a citizen or a permanent resident, right? And it becomes actually very easy to express this because you just express a disjoint with relationship between those two classes, right? And now your system will reason over this automatically. You can do the same thing for TSOD. This is flat RBAC. You're basically saying a person is allowed to access this if they are a full professor, right? And you can check that. You can do some reasoning and inference here now in role-based access control. So what if I said people who are members of the faculty are allowed to access this? What about someone who presents a credential, a role saying they're an assistant professor? Well, as long as in my ontology I capture the fact that an assistant professor is a kind of a faculty, is a subclass of faculty, I can reason over this, right? So ABAC captures all of this and adds stuff, and one of the things it adds is, for example, object attribute modification, constraints for object attribute modifications while you're running, and basically saying only certain people are allowed to do certain things at a given time. So this is about 2 years old, but it shows you something. This is where we actually are, and Chris has spent some time in Washington flying in and out of BWI, so he recognizes that this is I-95 right here, this is 195 coming from BWI airport, and we're right here. our campus. This is where we actually are. That's no fear. But we wrote a policy on our device saying, if Google Maps asks for our location, and this is a simple policy, tell them we're in San Francisco, right? And based on that system architecture I showed you, we're sitting in the middle. When the request comes, anyone here programmed in Android? So on Android, you can essentially capture Android's RPC mechanism is essentially intents. So you can sit there, listen for intents, and say, the map application just broadcast an intent to the GPS GPS service, wanting the GPS coordinate. We're sitting right in the middle. We capture it, and in this case, the policy is trivial. Tell them we're in San Francisco. We just read off the San Francisco GPS coordinates and send them back. Right? But this policy could be made arbitrarily complex. You could say, if Chris is asking, if the app owned by Chris, in this case, the apps are what are the subjects in the Android world. So you can say, if an app owned by Chris is asking, tell them we're here. If in some cases you might just want to generalize, the example I gave you earlier. Tell mom, I'm in West Lafayette, right? So randomly pick a point in West Lafayette and return that as an answer, right? So we sit in the middle. We take these complex policies, which are reducible to, which I showed you are reducible to traditional security models, and we change our stuff. And I think I showed you this earlier. It's unfortunately got duplicated. So what I want to pick from here is, as I said originally when I showed you the slide, I said the reason we want writing these policies is hard. Policy engineering is hard, right? Just like software engineering is hard and security generally is hard, policy engineering is hard. What's a good policy? Right? Should Apple be, releasing the information on that bad guy's iPhone to the government? Whether or not you do it is a policy. That's an example of a real policy that you have to reason over, right? And what happens in the real world? The policies are ambiguous. They're written in English. And the final word will come, in this case, I think, from the Supreme Court. A bunch of people interpreting that policy, saying this is what that policy really means, right? So policies can be very complex. And I want to just, as a little aside, tell you that this former student I was talking to about, Lalana, you know Lalana, right? Yeah. So Lalana's done some good work, where in one case, she took most parts of HIPAA and reduced it into something like this. For those of you who are not familiar, it's the health insurance, portability, privacy. Every time you go to a doctor, you have to sign something saying they've given you what their privacy policies are. And again, if you're like most people, you don't actually read that. The doctor gives you a bunch of forms, you fill your name in the right places and sign in, and you give it back. But you're actually agreeing that to whatever their privacy policy is, which I'm sure the doctor and his staff has no idea what it is. It's just whatever the IT guy gave them, right? So, and HIPAA is pages and pages and pages of United States code. So it's very complex. So you want to capture those kinds of policies. But when you start, you're probably not going to get it right. Right? So in the real world, you go to a court, you have judges rule, and you have courts of appeal, and then you have the Supreme Court, and if you don't like what's happened there, you can go back to the legislature and have the legislature redraft the law, or clarify the law, or you have agencies that interpret. Now in this case, who's doing all of this work? So I just painted a beautiful picture for you. Oh, policy-based access control, no problems, just write policies saying my mom is not allowed to do something, whatever. Well, how do you know that's the right policy? How did you write that policy? How did you start? And so that's a really hard and open question. There is some work that's beginning to happen saying, can you apply machine learning to this, right? Can you take the actions that a user does or does not do on their smartphone, for example, and infer from that what their access control policy is? It's a hard thing to do, but people are beginning to grapple with that problem, right? We're starting with something simple, right? We're saying, I may not know exactly what your policy is, but I might have a reasonable estimation, or the organization I come from would have a reasonable estimation. So Purdue might have a reasonable estimation of what policies it permits or its employees are supposed to follow, and which of those are subject to some change, right? You must fly on a United States flagged carrier. Whether you fly United or Delta or whatever is, maybe the default will say you will always fly United, but you will notice that, well, Chris in this case is flying his own plane, and you will say, well, there's an exception for that, right? The policy is amended. So what we've now built, and these are brand new, so you're seeing the latest version of Android here, right? This is Lollipop. What we have built is a thing where we start from a default policy. We let that policy run sort of in an observational mode, right? So the policy said, don't pick up calls when you're in a faculty meeting. And I notice you don't pick up most calls, but I notice that certain calls are picked up. So we capture what are called violations of the policy. And periodically, we report the violation to the user saying, boss, the policy you said that applies here doesn't really seem to be the case. There are violations. Now, because our policy is, one of the nice things, because we are capturing it in a formal model that is grounded on ontology and what is, so if the policy says don't pick up phone calls from anyone, you can say, well, what do you want to change? Do you want to say this rule is bad now? It's okay to pick up calls? You said don't pick up phone calls in a faculty meeting. Did you mean to say except for faculty meetings that happen in the month of May? Because again, we can do this kind of reasoning around whether certain constraints on the policies have to be relaxed or tightened, because those policies are drawn from this ontology that we have, instead of this formalism that we have. Or did you really mean that this phone call was from your wife or your husband? And that's why you're making the exception. So the rule should really say, don't pick up calls in a faculty meeting unless, right? So we guide the user through this process and give them options at various stages because it's drawn from an ontology. Did you have a question, Chris?
Yeah, one of the things that I see in this is, in order to capture that there's a violation, don't you have to not enforce the policy?
Correct. So
Okay.
that's what I'm saying. It's an excellent point in case I didn't make it clear. We start in an observational mode,
Okay.
right? Because once we start enforcing the policy, the battle is lost. The phone call will not be picked up. Your phone will automatically reject it, right? So we start in an observational mode, which has its own problems. Can you be in a relatively safe state for a while you observe violations? The only true answer to this is what I was telling you earlier, which is you have to have machine learning sitting there and gathering what you're doing. And even then, in any learning paradigm, you're initially operating in a safe state, because if I started with a default policy that was enforced, you wouldn't know what the user was doing anyway. So it's a good problem, but
I have a quick question about that learning state.
yes, sir.
Any thoughts on how long you'd let it run before you decide you have enough information?
Good question. That's what we're playing with right now. So you have this trade-off where you might want to say, I'll let it run for like a month and capture all possible nuances and then get the user to fix the policy. But then you run into, do you really want it to be let loose for a month without any protection? And so what we're looking at is sort of saying right now doing a daily update. But that's an interesting human factors issue. Is it you could do this every 10 minutes and say, boss, I just noticed, every time you notice a violation, you could go right up and say, boss, I just noticed a violation of your policies. Do you want to fix it? We suspect that people will not be too happy with something like that. So we've arbitrarily picked a day, but there's nothing sacrosanct about it. So for the systems types, yes, sir.
What about another phase where you do intercept like the phone call, but then you tell the user about it like later that night? Say, hey, we intercepted your phone call and we told your mom that you're, somewhere in Lafayette. Is this what you wanted us to have done?
So that's a good thought, and we sort of discussed it. The issue is that the issue is how close are you to the correct policy when you start, right? If you're reasonably close to the correct policy, then there will be a small number of violations that you can periodically report. If you follow the approach you've outlined, which is something we discussed, you'll have to report every action and say, was this the correct action? I picked up the phone here, was that correct? I didn't pick up the phone there, was that correct? Right? And so if it turns out that the policies are reasonably close and 80–90% of the actions are going to be correct anyway, then you're just blowing up the amount of feedback you're giving to the user. If you have no clue on whether your policy is correct or not, or you want to be in a highly defensive mode, then you can do something like that, saying I'm going to run the policy and report to you all actions and say whether they were intended or not. Yes, sir.
Yeah, I sort of meant, so you do your observational period, and then you do this probationary period or something, and then you go into full enforcement. I guess was kind of what I was thinking.
So that's a good thought. That's a good thought that, frankly, I hadn't thought of, which is that you start with some pure observation things. Then when you're reasonably certain that you're right, you sort of say, okay, I'm going to enforce the policy and report, right, stuff. And that's
essentially flip a switch and go from observing actions that occur to reporting actions that don't occur, which hopefully would then be few.
Good point. So this is, for some reason, doesn't like grad student animations. You can go crazy with PowerPoint, like we have here. So what I'm trying to show you here is, so I hand waved and said, yes, we can run this on a mobile device. And the answer is yes, we can. But that still doesn't mean that you say, who cares, this is a Snapdragon octa-core CPU, because there's still battery to be thought of, right? So what we do is, instead of reasoning on everything statically, one of the things that the general reasoner lets you do is to say, free reason over certain things and find all inferences and store them in a way that you can just later use them, right? So if you think about the context that I was describing in which you're going to reason over a policy, parts of those contexts are static. Your name is not changing. If you join a faculty position somewhere, you're there for at least 6 years. And once you get tenure, you're likely there for a long time. I can extend that to PhD students. Right? Once you become a PhD student, you're likely there for 5. So some of these things are slowly changing. So what you can do is you can take, I'm calling them static facts, but I should really be calling them very slowly changing things. You can take those stuff and the basic ontology, domain ontologies you have, and build an inference model and save it so that you can later you don't have to do that part of inference. Right? If you are an assistant professor, I can infer ahead of time that you're a faculty and store that. I don't have to do that inference every time. And then you get just the dynamic part and the context information. And this I've put here because the system policies can change. But if you're reasonably sure, if Purdue is a 100-something-year-old institution, it came up with a policy 100 years ago and it's not changing, you could move this to the part of the inference model that you pre-compute. I don't know why it's not moving. And the user-defined rules come in after system-defined rules for very obvious reasons. Okay, so how are we doing in time? 5:20 is when I have to finish?
Yeah, so you're doing fine.
Well, I'm not, because I have 30 more slides. But so I will skip through the 30 more slides and tell you this. Once you buy into this idea that complex context and policies defined over that context makes sense for security and access control, you can see other places where this applies. So I showed you this in the mobile domain, but let me show you a different domain. And I'll skip a lot of the slides now. So if you're from India here, you'll recognize some of the things. But you know, one of the metaphors that people are being I knew I was going to skip those slides. Otherwise, I would have changed them to, well, if in the state of Indiana, I would have said, if you're guarding the basket, you're facing the player. That's what you have to do, not guarding the basket by, you know, Caleb Johnson or whoever's the big guy right now should not just stand with his back to the players of the basket. Right? You have to observe. So what is happening right now, if you look at the state of the art in intrusion defense, is a lot of low-level sensors and a lot of flat screens that show various warnings from the sense data. And then this Superman, Superwoman, whatever you want to call, analyst sitting there, whose job is to make sense of all of this in their head. And what are they doing? They're reasoning over context and organizational policies. This is completely stopped. So I skipped a lot of the details, but what we do is we say, okay, we'll do the sensor work like everyone else. We get Wireshark data and host monitoring data and IDS data and IPS data. But here's something else we do. Because as people in our group, some people, my colleagues are experts in text analytics, we actually trawl the web to say who's discussing a new attack. That's another part of the context. So now think about this. What you really want the computer to do automatically instead of a single superhuman analyst is the following. Someone was describing a new vulnerability they have found in, let's just pick Acrobat, because this was an attack that was actually done successfully against the US. Someone has found a new vulnerability in Acrobat, and it has to do with malformed JPEGs. And I noticed that Acrobat is installed on my machine, system scan, and a process corresponding to that program is currently running, host process scan. And that process has opened an outbound connection. Why should Acrobat be making an outbound connection? Has opened an outbound connection, and it is to the DHCP zone of my local, DHCP address space of my local internet provider. Now, ComSci security types are putting these facts together in their head and say, this is not right. This should not be happening. That's what a good analyst does. But notice what the analyst just did. They reasoned over a bunch of contextual information. I haven't shown you policies yet, so let me add policies. One of the very well-known attacks, this was something that Lockheed Martin followed for almost 2 years from a nation-state actor that shall remain unnamed, but you can guess which one. 2 years, where they started, and for 2 years they were constantly sending in new malware with new vulnerabilities that had been discovered. Right? How did this start? This started because 5 of their scientists in the missile division, who are each individually brilliant, aeronautical, astronautical engineers, got an email from their professionals. It's like, Chris and Mike and Elisa and everyone simultaneously get a mail from ACM saying, you've been nominated for the Turing Award this year. Now, any one of them might be individually deserving of that honor, but all 5 faculty in the same area, in the same department, all being nominated for the Turing Award, if I'm Dan Trinkle, I'm thinking this is not right. Right? Dan knows enough about our department that he can figure that out. So this is a policy issue. and a context issue. Here's another version of the policy issue. This was a targeted attack on defense establishment in India about a year and a half ago. People got email about a travel that they had just done. So, after this, Chris might send me an email saying, send me all your bills or whatever for the travel, right? They got an email that said, apropos the latest trip you took to some reasonable place where they were normally going, here is the bill or the something. Organizational policy says that this travel is handled by the travel department. It should never be going to the individual users. So here's the reason where policies and context has to be dynamically reasoned over to figure out that something bad is happening. And I'll give you the final example since I'm almost out of time. So what we're doing is, I think was I was describing, capturing organizational policies and the observed state of the system and the context. And let me skip all this good stuff. So you've heard of the latest things about cars being hacked and things like that, right? So we're actually we're working with some of our computer engineers to put in hardware. We monitor the OBD data. We have our own sensors. But even if you ignore all this, right, and you just rely on data on the CAN bus, it's not that hard to write policies for the car that say, if the car is allegedly traveling at an increasing speed, while at the same time the RPM is decreasing and the door is shown open, this is not right. Right? So we add to this external conceptual thing. So there are sensors we put in. The problem with doing this in a car is, how do you trust that data? So in a cybersecurity system on a mobile device, there are at least some sources of data that you can trust, even if other sources are fudging. In a car, if someone has compromised the CAN bus, they can compromise all the data on the CAN bus. It was a very poorly designed system. So we're saying, can we add sensors? And in case you think this is a car problem, the car industry will fix it, the same bus is used on all the Navy ships. CAN bus is used on all the Navy ships. We're working with ONR and USNA right now to see if some of this work can be applied to ships. And someone who knows these things, I don't, assured me that the planes in the Air Force don't have the CAN bus, but they have a bus that is very similarly designed. It was designed to efficiently funnel packets with minimal response time between the control surface and the actuators, and there was no thought of some of those packets might actually be bad. So again, right, if you buy into this philosophy, what we're trying to say is, by observing the context and having policies that talk about the context in the sense of what is permitted and what is prohibited, you can actually do a better job of security than just the straight traditional access control models that work. So I'm out of time. I'll stop here. Thank you very much.
We have a minute or two for questions. Do we have any additional questions?
Yes, sir.
So the accelerometer and stuff in this are to implement further policies on top of the existing policies which are there, so that, like, if in case the accelerator stops moving, then don't stop the car, so that detects a hacker attacked it or something like that.
Correct. Right?
Okay.
So what we are saying is, we've tried to do this purely on the CAN bus sense data, and we can't, right? So we can build, this paper is currently just going out for review.
Okay.
So hopefully it will be shortly shareable. But we can, even using relatively elementary techniques like hidden Markov models, detect these kinds of contextual fluxes that represent an attack. But there we're assuming that the adversary is changing some data, but not completely thinking through the model and changing other data. So so we can say, if your system is showing the brake is pressed while the car is accelerating, you're getting wrong reading from the brake. But if I'm an adversary, I will show that the brake is pressed and show that the car is slowing down, even though it's physically not. So we're adding a few minimal extra sensors where we have the ground truth. We control those sensors. So we can say, a more sophisticated adversary is trying to do something bad.
Are your sensors passive or are they capable of some crypto?
Right now they are passive, but there's no reason why they can't do crypto. So one of my colleagues has just proposed, it's gone to Oakland, I don't know if it'll make it, because Oakland is really tough to get into, but he has proposed adding lightweight hashed max to the messages to, but again, that's reverse engineering the CAN. I mean, the current CAN bus will not. And the full weight of the car industry is to say there is no problem. And if there is a problem, don't tell us to change the CAN bus. Just if you can do something on top of it, that's good. Otherwise, don't bother us, because it's a huge investment right now in all these cars. All right, thank you very much. I appreciate your time.